If a Markov chain has a regular transition matrix, then there exists an equilibrium vector such that VP equals V. Okay? So first of all, think about equilibrium. Okay? Equilibrium is like it's balance. Okay? And by that I don't mean that the two numbers are going to be equal. I don't mean that the numbers are going to be equal. I mean more it like reaches a stable condition. It stabilizes. It's not going to change anymore. Okay, so V is your vector, and P, remember, P was your transition matrix. Okay, so you're gonna have like your initial distribution vector, and you're gonna have your transition matrix. That's really all we've talked about so far. Either you have your square transition matrix, or you've got your row vector that talks about how many are in each state. Okay, that's really it. That's all we've had, one or the other. So it says use the formula above to find the long-range trend. So example 3 is talking about the Johnson and Northclean example again. So we've got this transition. And so the formula above says VP equals V. Okay, so V is going to represent the initial distribution. Now remember, the first example I said, I showed you a couple of examples, and let's see, it started at 0.4, 0.6. That was a vector. Okay, that was the initial distribution for that problem. And then I showed you that maybe it was 0.75 and 0.25. That was a different initial vector. Okay, initial distribution. But right now, I don't have any numbers, so I can't tell you 0.4, 0.6, or 0.75, 0.25. I don't know what they are, so I'm just going to use variables. Okay, X will be whatever is the percent that goes to Johnson, and Y will be whatever is the percent that goes to Northclean. Okay, that's my initial distribution. I don't know what it is. It's unknowns. It's variables. Okay, but that's going to be my vector. All right. So if you take VP equals V, if you just take that equation, this says use the formula above. That's what I'm going to do. So I'm going to try to write kind of small if I can. That's V. Yeah. And that's P. And that's supposed to equal V. So write that down. VP equals V. That's the formula. Okay? That's it. Now, we have to go back and use what we know about matrix multiplication. Okay? Don't write this down. But I've got a 1 by 2 times a 2 by 2. Bless you. Which we know that will work. Those inner dimensions match. That tells me that the answer will be a 1 by 2, but that's what we have over there. Okay? We're talking about a matrix multiplication problem. That's what this becomes. And so remember how we do matrix multiplication. We do a row times a column. Okay? So your row times your column is going to end up equaling that number right there. So let's think about what we would have. If we multiply that row times that column, we're going to have 0.8x plus 0.35y equals x. Row times column, and it's going to equal that last thing. That's the first row. If you think about it, that's the first row times the first column, gives you the 1 entry of the answer. Okay? So then we would have to do row times column to get the 1, 2 entry. Okay, the 1, 2 entry comes from row times second column. So we can go blue row times blue column. That's going to be 0.2x plus 0.65y equals the 1, 2 element, which is y. So we have a system of equations. System of equations comes straight from that VP equals V. All right? Now, we're going to end up doing a Gauss-Jordan on this. Okay? But we need to do a little bit of a setup first, and we're not quite ready to do it. The website I'm going to use doesn't like decimals, so I want to get rid of my decimals. We've done this before. If you want to get rid of your decimals, what you can do is multiply by 100 in this case. So I'm just going to take both equations times 100. Just to get rid of my decimals, that's going to be 80x plus 35y equals 100x, and 20x plus 65y equals 100y. The main reason I wanted to do that is because it's easier for your brain to follow that, okay? I think you can probably see what I'm getting ready to do next is subtract the 100x over to get it in standard form. So if you subtracted the 100x over, 80 minus 100 is negative 20. That would give me negative 20x plus 35y equals 0. Similarly, I'm going to subtract the 100y over, and I would have 20x minus 35y equals 0. At which point, you might notice a little bit of a problem here. That's not right?
That's not right?
What's wrong?
You did the same thing on the bottom that you did top, but it's different numbers.
Well, you're definitely noticing a problem here, okay? There's definitely a problem, but I don't think I did it wrong. When I subtract 100x on the top, I'm definitely going to get negative 20x plus 35y. When I subtract 100y on the bottom equation, subtract 100y from both sides, I'm definitely going to get 65 minus 100 is negative 35. But what you're noticing is weird is the two equations are actually the same equation. That's actually only one equation. You know, think about it. Multiply one of them by negative 1 now. You're going to get the exact same thing as the other. Okay? So anytime you have more variables than equations, that's what I have right here, 2 variables and only one equation, it would be many solutions. Okay? So if you tried to do a Gauss-Jordan right now on this, you're going to get many solutions. Okay? But fortunately, we have another kind of constraint that leads to another equation. Think about what has to happen for every single one of these distributions. What do we know about x and y that's going to happen every single time? X plus y equals 1 every time, no matter what. Okay? Every time, no matter what, I know that x plus y in my distribution is going to equal 1. So I'm going to use that fact and just add in a third equation because I know it's true for my system. It has to be. So I say 3 equations, but really that's only 2 equations because one of them's going to run into the other. They're just combinations of the other. So let's just assume we didn't know it was 2, and let's just think about this as 3 equations. So if we got it into a augmented matrix, we'd have negative 20, 35, bar 0, 20, negative 35, bar 0, and x plus y equals 1 would be 1, 1, 1. Okay? So it's a little bit weird to have a 3 by 3, but we're going to do the Gauss-Jordan process on this. Okay? We can do that. I don't want to do it by hand, though. So remember what we can do. Let's go to the site that's going to help us do Gauss-Jordan. Okay? So this was a weird one. I don't think we've ever done a 3 by 3 before, but that's fine. Let's do a 3 by 3. Let's see what happens. If I'm going to do a 3 by 3 here, was negative 20, 35, and 0. Positive 20, negative 35, and 0, 1, 1, 1. So get your values typed in and hit solve. And this website's going to take us through that Gauss-Jordan process. Okay? So check it out. Oops, going to zoom. Notice the bottom row is 0, 0 equals 0. Okay? Don't make the mistake of thinking that automatically means many solutions. Okay? I only need two equations. When I have two variables, I need two equations, and that's what I show. If you think about it, if you had two variables and 50 equations, and you did a Gauss-Jordan with 50 equations, you're going to get 48 rows that have 0 equals 0 in it, because all you needed really was two equations. So as long as you have two equations with two variables, as long as you can see that x equals 7/11 and y equals 4/11, you've got your answer. As long as you can see what happens with x and y, you've got your answer is 7/11 and 4/11. So for my RREF, I might just put the two rows that I need, because I don't need that bottom row. It definitely doesn't mean many solutions, okay? But I've got my x and I've got my y. But remember, that's what my v was. That was my vector. That was my equilibrium vector, 7/11 and 4/11. Now, I know we're not as good with fractions as with decimals, so let's check it out, okay? 7/11 is basically that decimal that we saw before. Remember when we saw 0.6364 in the first example, and 4/11 was 0.3636? That's the fraction, okay? We like the fraction better because it's exact. That decimal was rounded off, but that's basically what you see in this example was a rounded off version of 7/11 and 4/11. We just didn't know it at the time. Okay, so that's kind of the process we're going to use right there. It might get more complicated, but that's basically it. I'm going to go ahead and stop that one. Otherwise, this video is going to be enormous.